This is AP Podcast 8.1, and we're going to talk about spontaneity and entropy. So the first thing is we need thermodynamics and kinetics when we're trying to describe a reaction completely. The thermodynamics tells us the direction the reaction goes. It compares the initial and final states, but it does not tell us how fast it goes. That's described by the kinetics of the reaction. So kinetics does the speed of the reaction, what was the fast step, what was the slow step, what could be a possible mechanism. It describes the pathway that the reaction takes. With thermodynamics, which is what we're going to focus on though, the first law of thermodynamics says that the energy of the universe is constant, energy is conserved. So it may be transformed from type to type of energy, so potential energy to kinetic energy to heat energy, but all of those are still types of energy, so the energy in the universe is constant, it doesn't change. A spontaneous reaction is something that will occur without outside intervention. So if I put two reactants together, that reaction just happens. I don't have to do anything to make it happen. And then a common characteristic of a spontaneous reaction is an increase in a property called entropy, which is what we're going to talk about. And entropy is abbreviated with the letter S. It's a measure of molecular disorder or randomness. So the more random or more disordered or more movement that something has, the higher the entropy will be of that molecule or compound. Entropy describes the number of arrangements, and arrangements could be positions or energy levels that are available to a system. The greater the number of arrangements, the higher your entropy value will be. You can think of entropy in terms of probability. So the higher number of probable ways you could arrange something increases the entropy of it. And the example here is a deck of cards. If I take a deck of cards and I just toss it up into the air, if it was before arranged by suit and by value, like ace through king, what we're going to see though when I toss it up into the air is that the likelihood that they're going to land exactly how I toss them is very, very low. You'd almost say it's nearly impossible, because the chance of them landing in a disordered fashion is much more likely because there are many more arrangements of them being in that random order instead of that one single order that I had them before I threw them up in the air. So the probability of a random order when they fall is much higher than the nice and neat ordered fashion I had at the beginning. So if we look at a gas here, the most likely arrangement is the most random. That means when I open this valve in the middle between these two bulbs, the ideal gas is not going to stay here, it's going to disperse. And that's because this arrangement has a greater probability of happening than this single arrangement right here. And we can see that even farther in this diagram. What they're giving you, they're calling it a microstate, but if you think of each of these as just atoms or molecules, you can see how many different arrangements are possible. But there's one here that has them all in the left-hand bulb and one here that has them all in the right-hand bulb. And so what we can see that is a random dispersal of the molecules is much more probable than finding all the atoms or molecules, whatever these are, in one bulb or the other. So it's nearly impossible, it's possible, but this arrangement, this random disorder that we would kind of appear to see in here is much more likely. And then you can imagine what we would do, say, if we had a mole of atoms floating around. This would just be so much bigger, and the random dispersion would just have such a high probability instead of the mole of atoms being found here or the mole of atoms being found here. So randomness is more probable than a nice and neat ordered fashion for these molecules. So if we relate entropy then to the states of matter, because we're saying entropy is this randomness, it's disorder, the entropy of a solid is going to be a lot less than the entropy of a liquid, which is allowed to move around, which compared to the entropy of a gas, the gas is much greater, and that's why they used the 2 caret signs here. So you can see that an entropy of a gas is much, much higher than a liquid or a solid, just because of the motion of the movement and the number of arrangements you can have of the atoms or molecules. And then this is relative entropy of reactants versus products. So if these were my reactants and they were going to these products, we can tell just by looking that this container has a much higher entropy before they react, and these have a much ordered or more ordered structure, so they have less entropy. So practice problem 1 says, for each of the following pairs, choose the substance with the higher, which would be more positive positional entropy per mole at a given temperature. So which one would be more chaotic, more random? And if we were looking at solid carbon dioxide compared to gaseous carbon dioxide, we would know that the gaseous carbon dioxide would be much higher in terms of its entropy because it can move more, and we know gases have more entropy than solids, so that would be the one that has the higher positional entropy. Nitrogen gas at 1 atmosphere versus nitrogen gas at 0.01 atmospheres, we actually choose the one with a lower pressure because a lower pressure means a larger volume, and a larger volume means more disorder. It means more probability or more probable locations for these gases, more different arrangements that they could take. So a bigger volume actually has a greater positional entropy per mole than something with a smaller volume, and usually you can tell that by just looking at the pressures. All right, the second law of thermodynamics says the entropy of the universe is always increasing. So energy is conserved. The second law talks about the entropy of the universe is always increasing. The universe is becoming more disordered, more chaotic. Everything is becoming more random. It's not becoming more ordered in the universe. Everything is becoming more disordered. So in terms of the reactions, though, we use this. So when you see delta S of the universe, we're not talking the universe as a whole. We're really talking the system that we're looking at and the surroundings that are around it. So we're more in the micro universe. We're talking about little universes, not the big one. And what this question says is, what does the sign of the entropy of the universe mean? So if the delta S of the universe is positive, that tells us that entropy is increasing and the process is spontaneous. So if we have a positive entropy, it means entropy is increasing and the process is spontaneous. If our delta S of the universe is negative, then the entropy is decreasing and the process is spontaneous in the opposite direction. That just means it's not spontaneous. And then delta S of the universe, if it's 0, it tells us that the system is at equilibrium. So that was for delta S of the universe. The other one that we're going to quickly look at is the sign of delta S of the surroundings, which is this guy right here. If the surroundings are positive, that means we had an exothermic reaction. So if we think about that for a second in terms of the system must have been releasing energy into the surroundings, and the surroundings were getting that energy that was being released, and they were becoming more disordered. So that's why the delta S of the surroundings is positive, because they're picking up that energy from the exothermic reaction and becoming more disordered. If delta S of the surroundings is negative, then we had an endothermic reaction. The system or the reaction was pulling energy in from the surroundings, which makes the surroundings lose energy and become more ordered, so delta S is negative. So the next thing we're going to do is look at this reaction. We have liquid water going to water vapor. It says, what happens to the entropy of the water? Well, water is going from a liquid to a gas, and we know because we've already talked about it that a gas has more entropy. So this would be increasing. The entropy of the water is increasing. It's becoming more chaotic, more random, because gases have more movement than liquids. So delta S of the system is positive. What's happening to the entropy of the surroundings? Well, it's requiring it to pull energy in from the surroundings. So the surroundings are losing that energy that's going into the system. So it's decreasing. It's becoming less in the surroundings. So delta S of the surroundings is negative. It's losing energy because it's going into making this reaction happen. So the system is gaining entropy and the surroundings are losing it. What about the sign of delta S of the universe? Well, this is actually temperature dependent. It depends on what that temperature is, whether this is spontaneous or not. So delta S of the universe is going to be positive. This is going to be a spontaneous process if the temperature is greater than 100 degrees Celsius, because this will spontaneously happen above 100 degrees Celsius. The delta S of the universe is going to be negative if the temperature is less than 100 degrees Celsius. So greater than 100, this will spontaneously happen, and delta S of the universe will be positive. It's going to be negative if the temperature is less than 100 degrees Celsius. And then temperature and spontaneity, this kind of just goes over that. Entropy changes in the surroundings are determined by the heat flow. So whether it's going in or out of the surroundings determines what happens to the entropy in the surroundings. An exothermic process is favored because by giving up heat, the entropy of the surroundings increases. They're going faster, they have more entropy, and that's something that is good for the surroundings. So they like exothermic processes because they produce that heat that allows the entropy in the surroundings to increase. The size of the delta S of the surroundings depends on temperature, and that's kind of what we just talked about there when we were talking about the sign of delta S of the universe for the water turning into water vapor. What we have is this little formula right here that we can look at. The delta S of the surroundings is equal to, this is the enthalpy of the system divided by the temperature. And they put this little minus sign in right there because that changes the point of view from the system, which is what delta H is measured for, to the surroundings. So if delta H were negative for the system because it's exothermic, it's going to end up being positive, and it will make enthalpy it'll make entropy positive for the surroundings, which means it's spontaneous. So the minus sign just changes the point of view from the system to the surroundings. And then one of the last things we're going to talk about here is this little table that compares the sign of the system to the surroundings to the universe. And what we know is that if delta S of the universe is positive and delta S of the surroundings is positive, then the system is also positive. If all those things are positive, we're going to see a spontaneous process. So this is a yes. If everything is negative, we are not going to have a spontaneous process. It's not going to happen. And then these get a little trickier. So if we remember that delta S of the universe was equal to delta S of the system plus delta S of the surroundings, if delta S of the system is positive and delta S of the surroundings is negative, the only way that this is going to be positive is if this system part that is positive right here is greater than this negative part. So this is yes if delta S of the system is greater than delta S of the surroundings. So you need the system to be bigger because it's the one that's positive, which means this last case right here would be the opposite. In order for this to be a spontaneous and for delta S of the universe to be positive, then we need the surroundings to be larger. Oops, that should be a comma. If delta S of the system is less than delta S of the surroundings. So positive entropies, good thing. They mean that we have a spontaneous process. Things are becoming more disordered. And that is it for podcast 1. So just understanding this idea of entropy and what it means, whether it's spontaneous or not, and how you can relate the entropy of a system to the entropy of the surroundings, and then also overall to the entropy of the universe.